Alright, so let's say we've got an election going on. We have done this before, despite what you may think. We have an election going on. We've got a lot of money in the game, right? We're heavily invested. If one party wins, we lose a lot of money. If another party wins, we make a lot of money. And we need to know whether we take our investment out now or not. There's 1 million people involved in this election. We've got to vote for person A or for person B. Person A is the one that makes us a lot of money. Person B costs us a lot of money. So to get an idea, we have to go to the public and to find out what they're going to do. And we have two options. We can either ask 1 million people who they prefer, or we can do a smaller survey of 100 people. Which would you choose? Smaller survey. Why? Because if the election was 2 weeks away, it would probably take you 2 weeks to get the first 100,000 people asked. Correct? So it's going to take way too long for us to do it, so we do a smaller survey. If I wanted to be more accurate, what would I do? Increase my sample size. So I've got a survey of 100 people, but if I wanted to be more accurate, I would increase my survey size, and we'll talk about why that's the case. But here we are. So I've got, this blue bubble represents my whole 1 million people, and the little red bubbles represent what? What do they represent? A sample. It's 100 people each bubble. Okay. The first bubble I ask gets 0.56. The second bubble, or the second 100 people, say 0.56. Third gets 0.58. Let's say. What I'm trying to get at here is each sample proportion, because that's that p hat. Each sample proportion will have a slightly different number. Correct? Yeah. But it'll be pretty close to our population proportion. If I was to get all these different sample proportions and distribute them, what would happen? How would it look? If I was to get all these sample proportions and put them on a line like this, how would it look? Like a normal distribution, correct? We know that from our sampling proportion. Where would we expect our normal distribution? Or what would be the mean of our distribution?
The average of those.
Yeah, the average of those, which would be what?
0.56
Plus 0.58. Plus, but I have to do that the other, 10,000 times.
Wait, what?
What would be, if I'm getting all the sample in 1 million?
Yeah.
If I had, I'll just pull it up. How many of these proportions, sample proportions, do we expect to be above our population proportion? If it was a perfectly continuous bit of data. How many? I'd expect about half of the, okay, what do you reckon the population proportion is looking at that? Looking at the data we've got. What do you reckon the true number of people that are actually going to vote for candidate A are? 0.56? Anyone have anything different? 0.57. How do you get that?
Just
Between them. So we would expect the population proportion to be in the middle of all our sample proportions, correct? So the true value will be the mean of all of our sample proportions distributed, correct?
Yeah.
Happy with that? Now if I have a population proportion, so if I have this big population, how many of my p hats will lie within 2 standard deviations of my population proportion? So how many of these scores will lie within 2 standard deviations of the actual value?
Like
90,
something,
95%, correct? So if I was to pull out a proportion, there's a 95% chance that it's within 2 standard deviations of the actual value. Does that make sense?
Wait, is P the actual value?
Actual value.
And P hat, what's P hat?
Sample proportion. So like the score for each one of these groups of 100.
Okay.
Sweet?
Yeah.
So what I'm trying to do with this is to say, well, I know a sample proportion, I know the score of my sample. How likely is it that the true value lies within a certain range? Cool? So that's what we're trying to get at here. Now the standard deviation for this distribution, as we know from sample proportions, is equal to the square root of p 1 minus p over n. We've seen that before, haven't we? So if we increase, and that's what Brody was saying, if we increase the sample size, we can't change P, can we? We cannot change the proportion, that's just what it is, but we can change the number of people we sample, N. The larger that value gets, what happens to our standard deviation? The smaller it gets, correct? So the smaller our standard deviation gets. As our standard deviation gets smaller, our confidence interval also gets smaller. Cool? So we get more and more certain of what's going to happen. Is everything that I've said so far okay? Just to summarise in case we're not, confidence intervals are all about saying if we know our sample value, sample proportion, how likely it is that our true value falls within a certain range, certain number of standard deviations. Cool? So all of this has been about sample proportions, and now this is where the standard normal distribution comes in. So this is where the Z-scores come in. And it's about saying, well, that's that 95% that I was talking about. If I want a 95% confidence interval, what's the Z-score that gives me 95%? 2. Now remember, what are Z-scores? Z-scores tell us, it tells us how many standard deviations outside our mean. So if we've got a Z-score of 2, we're 2 standard deviations above the mean. Correct? If we've got a standard deviation of -3, we're 3 standard deviations below the mean. Cool. So I set my standard deviation, my Z-score, depending on how confident I want to be. I set how many standard deviations depending on how confident I want to be. So if I want 95% confidence in, so if I pull out a say this 0.56, and I want to be 95% sure of my, I want to know what my population proportion is within 95% confidence. Let's say my standard deviation here, just hypothetically, is 0.02. I'd have to add 2 standard deviations above and 2 standard deviations below. So I'm 95% confident that the true value lies between 0.52 and 0.6, sorry. Does that make sense? So my proportion was 0.56 here. I pulled that random number out. I've got 100 people sampled, 56% of them say, my standard deviation, I've used this equation, my standard deviation is 0.02. I am 95% sure that the true value is between 52% and 60%. Cool? Which means I'm 95% sure that my investment was a good idea. Keeping my investment's a good idea. Happy with that? If I want 68% confidence, instead of making 2 standard deviations, I'd make it 1. So I'm 68% sure that it goes between 0.54 and 0.58. Now I've got trillions and trillions of dollars in this investment. How much should what should be a confidence interval that I'd like to set? 95. You reckon 95 is enough? 99, you reckon 1% chance of losing $1 trillion?
Yeah, sure.
Yes.
Okay, you happy with that?
So we just gambled on a quarter odds over here.
I like 99.7%. What should my standard deviation be? 3. So I want 3 standard deviations. What will be my confidence interval? .05. I take 0.06 off. So 50% to 62%. Sweet.
Wait, that's your confidence.
That's my confidence interval. So I'm 99.7% sure, given that my score of my sample proportion was 56%, I'm 99.7% sure between 50 and 62% of people will vote for Party A. Which means investment's good. Keep your money. Cool?